the trenches of motorsports and Gearhead Central. This is RealTuners Radio, your all-motor, boosted, and nitrous-fed hour of power. Now, here's your hosts, the Reverends of RPM, the Faction of Traction, John Bewley, Scott Clark, Bill Fowler, Scott Evans, Mark Dahlquist, Mike Perduto, James Short, Tom Sewell, Brian Barnhill. This is RealTuners Radio.
All right, everybody, welcome back to RealTuners Radio. What's shaking? So it is Wednesday, August 26th, 2020, and Bill Fowler's making a bunch of background noise, kicking it off for you. Thanks, Bill. No, let's see. So welcome back. It's been a week or two, whatever, and it's really, really special guest tonight by request. I know so many of you guys have been requesting that we ask Mr. Darin Morgan to get on the show at some point, because really it's right up his alley. And so I just happened to message him this morning thinking maybe I'd get this guy in the next couple of months, and he was open tonight. So here we go. I'll go ahead and introduce him here again. Hey, Bill. What are you doing? Doing a workout?
Everybody, it's a little early, but everybody take a drink.
I'm going to go ahead and mute him anyway. There we go. I muted him. Okay. Sorry, Bill. Anyway, so just wanted to extend a really warm welcome to our really one of the country's top induction system design and tuning specialists. I think as an EFI calibrator, that's probably what I would call him. We go to guys like him or him when you really need your airflow, your induction system to complement, combustion, keep that volumetric efficiency as high as possible, that kind of stuff, for as broad a power band as possible. So you've heard us talk with Chad Spire a couple times early on in the podcast. This is the guy that Chad looks up to and gets lessons from. You can take classes from him. So anyway, welcome to RealTuners, Mr. Darin Morgan. How's it going?
Good, real good. Thanks for having me.
No, thanks for joining us. We really appreciate it. So if you could give us maybe a couple minutes or however long you like, we've got all night, a little bit of background about kind of how you got into what you're doing and how you ended up where you're at.
I was born into it. My fathers were both engine builders and drag racers, so it was just natural that my brother and I, Brad Morgan, who works at Darin Morgan as a head engine builder, would take this up as a profession. I crawled on the flow bench at the age of 18. My father didn't want anything to do with it, and soon found out that I didn't know what the hell I was doing. And actually, the first set of heads I ever ported lost 40 horse. So that's normal. And I don't know, it took me good tutelage early on. One of the guys that used to work at Darin Morgan under Shepard kind of took me under his wing and taught me about throat sizing and airspeed and stuff like that. So I got a huge head start in that regard. And then working for a team, Gary Herman in Pro Stock. And then I went to MagCap, and then I went to Darin Morgan's, and I went to Bob Glidden.
Okay, so that was a pretty quick move through that. Why, I guess, what drew you to airflow or optimization? I mean, at that point, I guess it sounds like you were working on big inch naturally aspirated stuff.
Yeah.
At that point in time?
Got my start in comp eliminator, with Super Stock, then comp, and then Pro Stock. Right off the bat. So I got a huge head start.
Maybe get the big block Ford stuff out of the way before we get to most of our listeners, it seems like, are turbo LS guys. And I think at their budget level, one of their bigger questions is going to be what's worth optimizing or looking at on a budget, for their kind of
I thought this entire night was going to be
maximize.
I thought the entire night was going to be devoted to big block Ford. I don't understand.
And I'll be quiet.
Kidding. I think the question, because our audience do tend to be guys that aren't, stepping off with, well, I'm going to spend $50,000 to $80,000 on a motor from scratch. They're usually people that are building off of some sort of existing combination, starting all the way back at the usual sort of, well, I don't know if there are any more junkyard LSs, but that's where a lot of people have been. But when you start stepping into cylinder heads, the next question becomes, do I get something off the shelf, or what are the benefits, and what can I get by thinking about something a little more custom, and how do I select that head?
How do you select the cylinder head? Well, well, that's the trick question. I mean, really, it depends on the engine, its intended use, for one. I mean, take a stock LS7, you're not going to turbocharge that thing, try to squeeze 1,000 horsepower out of it with stock cylinder heads. You need something stronger. That's not to say that those cylinder heads, the stock OEM heads, are not capable of that. They are, actually. I mean, 400 CFM cylinder head will make 950 horsepower with the proper cam and induction system. And I kind of always laugh at people that want these 400 CFM cylinder heads on a street car, and all they're doing is just murdering the low-end power band in order to get that one big blip number up high. When in actuality, the stock LS7 port cross-sectionally and from an airspeed standpoint, it will sustain 900 horsepower easily. So basically, a lot of people don't need one as much flow as they think. They need a stronger cylinder head, or a cylinder head designed for a better valve train, something that's going to live in with that engine in its intended use. I hope that makes sense.
Yeah, I think it does. You might want to expand a little bit, especially around valve train, as there is a lot of discussion these days, especially with turbo combinations, about where the improvements are and what's necessary. Is, can you do everything you need to do with stock rockers? Can you do everything you need to do with stock shafts? Can you, all those type of considerations. Mast is known for having some of the most capable cylinder heads made for that platform. So I'm going to ask the most difficult question: cathedral port or square port?
Well, let's look at what an engineer, an OEM engineer, has to do first. An OEM engineer has to work within this box, okay? Low hood clearances, low profile, and he has to fit everything in that box. This is where the LS platform came from, the cathedral port. It's a very low profile port in order to get the manifolding and the length tuned properly. It's not that that port is designed light years ahead of anything else. Actually, it's just designed to fit within that box. There's nothing magical about it. I mean, a square port or an oval port that's raised where it's short side, the LS port comes in, the short side is like right here, the LS port floor comes in like this. Any port, high performance port, I guess you would say, has the floor at the very least even with the apex to the short turn. So the only reason those ports are designed that way is so they could fit the manifolding in under the hood. There's no magic there whatsoever. And the square ports, their LS7 style raised port, will make far more power than a cathedral port will.
I've always been told, and John's not on tonight, but the square port versus cathedral port in boosted world, it has nothing to do with the port. The port's meaningless. That is how a layman we can describe where valve location is in the cylinder. So it's not a port deal. It's a valve location in the combustion chamber that moves when you make that port change. And that's just how, as a layman, we make that discerning factor as to which head's better.
So expand a little on what you mean by valve location.
I honestly don't know. John has a theory on that. I wish he was on. It's something to do with where the valves, I don't know if they spin the valves in the chamber or what they do, but where, from what he explained to me, where the valves are located in the cylinder on a square port and on a cathedral port are in a different location.
Okay, I'm not quite following.
It sounds like he's talking about the actual valve spacing and the orientation and clocking of the valves inside the chamber.
I thought he was talking about the turn of the intake tract as well, that it was more direct.
I wish John was on to explain his theory there. All I know is when he makes the I love square ports for boost, it has nothing to do with the port itself or his cathedral ports. It has nothing to do with the port itself. It's everything to do with basically combustion chamber design of the head.
I mean, if you're speaking, talking about the difference between a cathedral port with a 2-165 valve and an LS7 port with a 2-200 valve, of course, the power potential of the LS7 is much, much higher.
It's a theory he's talked back and forth, and I got on his case one time about it because I was like, it's nothing to do with the port. So I wish he was on here to explain why and how he came up with that.
I always tell people that I'm a velocity man, not a head, because that's what I do for a living. So if you have a port from roof to floor where you have 80% of your velocities on the roof and only 20% on the floor, all the reversionary signal, all the bad pulses in the intake tract are going to act on the low velocity area. But fuel will fall out of the low velocity area, and your wet flow, your air fuel mixture is not going to be as homogeneous. So when you raise that port up and you get your velocities from roof to floor as even as possible, it will carry that fuel more homogeneous into the combustion chamber and make a lot more power, even if you don't change airspeed, cross-sectional area, valve size, or anything else.
Just by making sure that the velocity is the same across the cross-sectional area? Is that what I heard?
Yeah, you try to equalize it as much as humanly possible. It's in a perfect world, you would want, at the choke, you'd want it 300 at the roof, 300 to the floor, and in every corner. Well, that's not going to happen because the airflow path is like it's electricity. It chooses the lead path of least resistance, right to bore center. So the highest velocity areas will be on the roof and on the straight wall or bore hole side of the intake port, which causes a gradient across the short side, makes low airspeed, high airspeed over here. That's where the fuel falls out in the low airspeed areas. So my job is to take that area, manipulate it, camp the short side, and do everything I can to make that as even across there as I possibly can to carry that fuel into the combustion chamber.
All right, real quick, there's a question coming in across Facebook. Let's hit on the differences in induction for wet flow carb versus wet flow port injection versus direct injection. And he says, and toss a little diesel theory in there if you got it.
Oh boy, you didn't ask for much.
No, not at all.
Carb wet flow. Back in 2000, Joe Mello came up to me at PRI and said that he had a wet flow bench design. And he asked me what I thought of it. And I said, well, they're pretty much expensive play toys because you can't see anything. We put food dye in it and use strobe lights and everything else, but you can't really visualize it. And you definitely can't see the small atomized cloud coming out. So he had an idea to introduce an ultraviolet liquid with 50% water and 50% alcohol to lower the specific gravity of the fluid. And it's unbelievable what you can see. The pictures that I've posted on the internet over the last decade can't do it justice. You literally can watch the fuel droplets come into the port, and right at the apex of the short turn, which is the highest peak velocity anywhere in the induction system, right at the apex of that short turn. So the port comes in and then turns. So right there at that turn, the airspeed spikes right here at the short turn. Purposefully, we do this, that airspeed has to be a certain amount, or it won't do one thing. It won't pull the fuel around the corner. It just slams into the back wall. You can literally watch the fuel droplets come in, and as soon as it hits that high velocity area, they turn 90 degrees and go straight down. It's the wildest thing you've ever seen. So after we started looking at this, we started making manifolds that were clear and cylinder heads that were clear. I had heads cast out of resin, clear resin. So I could literally go in there and put lights and everything and actually watch it go through the system. What you see is anywhere, again, that there is a velocity gradient where the air slows down. Let's say you have a runner that bends around a corner. All the fuel is going to try to slam on the outside wall unless you can make that bend velocity correct to pull the fuel around the corner. And what you see is anytime you have fuel separation, it will just form trails, just trails running down those runners. Now, all that fuel that's fallen out of suspension doesn't burn. Well, it burns, but it burns too late to create any usable cylinder pressure, and it just goes out the exhaust as hot gas and heats your components up, valves, everything else. So what we learned is from watching this was when you have a carburetor, the air speeds the height of the venturi from the opening of the runner. This is a secondary tuning variable where that is. The length of the barrel is also a tuning variable. And when that comes out, you want that airspeed right at the opening of the runner to be 220, 240 feet per second, no lower than that. Otherwise, you can't turn the air into there. The radiuses around there form a shear to shove the fuel into the center of the runner. So those radiuses have to be just fine. And everything has to be rough, rough, rough. In a plenum, in like a pro stock deal, I would put 36 grit in there. And then slowly down the runner, I wouldn't even get to 60 grit until I got to the port opening. And Chad is doing what they call bird manifolds. It goes in there and does a burr finish, and it looks like hell. I mean, so for some reason, people think that heads need to be, or an induction system has to be aesthetically pleasing and for it to work. It doesn't. Chad has proved that over and over again. I mean, those manifolds are all 4 to 6 horsepower more just by keeping the air fuel mixture suspended in the airstream. I mean, you're always going to get some degradation of the air fuel mixture.
So Darin, I'd like to add something right at this moment, because we're talking about keeping the air and fuel suspended in the airstream and how it pulls through the carburetor. And of course, the carburetor itself does a great job of homogenizing the air and fuel as it pulls it through the booster. What about when we go to throttle body fuel injection? What happens?
Throttle body fuel injection.
Yeah, so now we don't have a venturi. We've got a couple of injectors, and we don't have great atomization, and we've got a manifold floor right underneath it.
Well, there are ways to help that situation. It depends. I mean, if you have the barrel here and the injector, like the old TBIs, are right over the barrel, the fuel shear, the actual change in velocity into that barrel will shear the fuel droplets. And you guys can actually witness this. Just take a wet flow vac, turn it on, and pour water down the tube and watch it. As soon as it hits the high velocity, it will immediately blow apart. So you do get a little bit of atomization from that. The best way to do it, of course, stick it in the side, stick 4 around the side and spray it directly into the airstream. And then you've got 2 velocities coming together. And then that's when it atomizes the best. And you put the injector on the side of the runner. So you wouldn't put the injector here, you'd put it over here so that the air comes in and immediately turns it into the runner. That's the best TBI setup I've ever worked with.
So taking Mark's question one step further, what happens now when we're dealing with typical port injection where the injector is sitting just up over the face of the manifold where it meets the cylinder head?
Oh, I got lots of stories on this one. The OEMs put the injectors where they do, right down at the port opening, right at the valve cover rail, because that's where it fits the best. It's definitely not the best place to put it. The best place to put it is where the Formula One guys put it, in the plenum, right over the runner, to where the spray pattern encompasses the entire opening of the runner. There's lots of videos on the internet you can go watch. That is the best atomization you can possibly get right there. But most people will just put them down the runner. And what that does, it does multiple things. When you have atomized air fuel mixture going into the runner, instead of halfway down the runner, you've increased the charge density. In other words, the whole runner, like on a carbureted engine, is full of air fuel mixture. Well, on an EFI with the injector load, only half of the runner is filled. So you have basically half the charge density, so you get less inertia supercharging effect. It's harder to raise the pumping efficiency and get a higher VE that way. And also, it's harder to atomize the fuel because you have 1 less time. And 2, you're not introducing it into an area that can center the air fuel mixture. Like when you have it going into a runner, the radiuses around there, the air fuel mixture doesn't hug those radiuses. It shoots off a little bit. So your signal is what we used to call it, or your air fuel mixture cone is, if your runner's this big, it's in the middle and it's about that big. In a perfect world, that's what you would want to do. But when you're spraying down the runner, you're spraying all over the walls. You're deatomizing the mix right off the bat. So even the best, highest pressure injectors have a real hard time producing power. And as a matter of fact, on a Pro Stock manifold that I did 2 years ago, the runner is like this, and the injector wasn't here. It was here, and it was aimed up the runner. It was shooting the air fuel mixture back up into the plenum so it could atomize and then take it back into the runner. And that's power, but it was not tunable because one runner would take more fuel than it wanted. It was tunable within from torque peak to horsepower peak when you're in a tuned environment, but it's below torque and above peak power was a mess. So placement is all about getting the highest charge density and the best atomization possible. I didn't get off track there, Dave.
Just on that, when you're talking about placement, when you start incorporating transients and low throttle, when you streetcar stuff, especially what we have to worry about on the OEM engineering world and stuff like that, where would you see that? Because the traditional, what I've always heard and seen, and what is even beating our head when I was in the OEM world was, oh, well, up there in the runner, yeah, it's great for high RPM, it's great for power, but transients and idle and emissions is just impossible with
yes,
runner.
You're correct. You are correct, 100% correct for transients and throttle response, and that it's horrible. Yeah, putting it in the plenum. Which is why these circle track guys put down nozzles right in the port, because it's instant throttle response off a corner.
And that would make an argument for having two sets of injectors.
Yep. I mean, that's why you see your high RPM engines, especially your high strung race engines, or street bike engines. Now, almost all street bikes run dual injectors.
Street bikes, yep, for sure.
I don't think you can buy a lawnmower without EFI anymore.
That's hard. I mean, there's snow blowers and stuff up here with EFI now.
Well, they got chainsaws with EFI.
You mentioned atomization a bunch. What about the fuel hitting the back of the intake valve? What big effect does that have on all of this?
Okay, let me touch base. Well, one more thing on injection, and then I'll get to that question. Earl Wooden had the streamliner. Actually, it was this streamliner, the Spirit of Ret. He owned it before Nearberg set the record with it. And he came in and he kept it. This was an alcohol injected, mechanical injected engine. He couldn't get a run. It'd blow head gaskets every single time. And this is on alcohol, by the way. This is a normally aspirated engine on alcohol, and he's detonating alcohol. How do you do that? This is a perfect case scenario of what happens when you put the injector in the wrong place, use the wrong injector at the wrong pressure with a poor atomization cone. And basically, mechanical injection, you might as well piss down the runner because there is no atomization with mechanical. It's horrible. So he had the injector so low and the wrong injector at the low pressure that it wouldn't atomize at all. So at that point, all you have is a ball of fuel on one side of the chamber and a lean area on the other, and it goes bang. So we moved that injector up into the plenum, and this is not overstating, it gained 110 horsepower. It was unbelievable. Just atomizing it, just 8 more inches. That's all it needed. So to your question, please repeat that question.
Mark, I think he's talking to you.
No,
that was Tom.
My question was, sorry, I'm driving. My question was, you mentioned atomization a bunch of times. What effect does the fuel hitting the back of the intake valve have on that?
Anytime the fuel strikes the surface, it's going to deatomize, period. The whole idea is to get that boundary layer on the wall as far off of the wall as you can to try to minimize that. You're never going to get rid of it all. So when it strikes the back of the valve, it does deatomize, but that's what the back cuts are for. And that's one of the reasons the back cuts are so powerful. Take, for instance, you buy a Manley valve out of the box. It's got 110 wide 45 on it. You back cut the valve with a 30, and make both of those equal widths. Now you have 2 shear ridges. Now on the wet flow bench, you can see this. It sticks out like a light bulb. Around those edges, all the way around there is a fuel shear ridge. And the sharper those are, the more it will shear. Now, there's also an increase in flow because you're tuning that venturi section up. So you get the added flow and you get the added shear, and that is always 10 horsepower at the very least. Just back cutting that valve is 10 horsepower every time. And that has 2 things. It gains about 10 CFM, and the fuel shear, the wet flow, improves dramatically.
The intake valve, not the exhaust, people.
The valve, yes. Yeah, I've never found back cutting a valve exhaust helping anything, to tell you the truth. Does that answer your question?
I believe it did. You guys see that one question?
Tom muted himself.
Shark fin? No, I think I muted Tom because he's being noisy. Sorry, Tom. Did you guys see that question? Was it on Facebook about why does he do the shark fin or maybe the wing? I think they used the term shark fin. I don't know if that's right. And how does he aim it? How does he decide how to aim it? Can someone see that question? I'm sorry, I don't have access to it anymore.
The wing on the floor, and that's not my idea. That was Bob Glidden's idea. He used that for many, many years. What that does is it's not a flow trick. It's not something that I do to improve the flow. It improves the wet flow. Again, we're talking about the velocity gradient and the fuel dropout. And the worst place that happens is on the floor. There's just huge trails of fuel just rolling along that floor. So if you have a flat short side, and let's say you actually do attain an even velocity across there, that will also help atomize the fuel as it goes around. But if you build a wing right there, you can actually lower each corner and actually lower the short side a little bit, spike the airspeed right in the center. And what it does is it takes all those trails of fuel, joins them together, and spits it right back in the airstream, right into the valve stem where it's split into the combustion chamber. And in a lot of cases, it can be anywhere from 2 to 4 horsepower on the average. That doesn't sound like a lot, but it does improve the burn that much. Now, I will say this. You can't just take a port and stick that in there and have it work. The whole port right there at the apex of the short turn, that area and that shape, especially the shape, has to be designed for that wing. So when people say, well, I put a wing in there and it didn't do any good, that's because you didn't, usually they got a square opening right there. Well, if you put the wing in there, you got to take this one, and that's what the port looks like. It's actually a diamond, a triangle shape. Because what you're doing is instead you're taking that square and you're making it wider and you're bringing the roof in, and then you're putting that wing right there on the floor. So think about it. Where's all the airflow, or where's the airflow want to be? On the roof. And it's not on the floor. So you have low airspeed on the floor where the fuel drops out. So you make it wider right at the apex. The apex is the fastest. The floor is the slowest. So you have slow moving air hitting this super high velocity area. So with the wing, you can broaden that out, and now it would be too big. So since you bring that in and the airspeeds actually even out, it'll actually take all those velocity gradients and even them out. So instead of having 220 or 240 on the roof, you've got 280. Instead of having 380 on the floor, you got 350. So again, in a perfect world, you're never going to get a perfect world. All we're trying to do is get it the best we possibly can.
Let's talk a little bit about, I wanted to touch on something because we're talking about the LS7 head, 400 CFM being worth 900 horsepower. I'm going to say since I was a kid, I've always been told that if you want to pick a cylinder head for an engine, 2.2 CFM per horsepower is just a generic number to look at. Is that about where you were going with that?
But it depends. That's true. An unlimited racing engine, right? Normally aspirated, carbureted, or fuel injected racing engine on gasoline, on racing fuel, can achieve about 1.67 foot-pounds of torque per cubic inch, period. That's all there is. There's only so many BTUs of energy in the fuel, so that's all the mechanical energy you're going to get out. So in Pro Stock,
very important point to make here is that's how you can tell if somebody's bullshitting about their engine dyno results. Right away, you can basic math here real quick and tell what category it falls into.
Very important part to make is we did 1.63.
That's
yes,
good.
For an Engine Masters Challenge project we worked on. Carry on.
And the torque per cubic inch is directly relative to VE, of course. And those engines, those unlimited engines, will produce 1 horsepower per every 0.395 CFM of airflow. Yet a street engine will produce a horsepower for every 0.55 or 0.55 horsepower per CFM of airflow, where an unlimited engine will be 0.395. Pro Stock engines, competition eliminator engines, IHRA Pro Stock unlimited engines are all 0.4 to 0.395 horsepower per CFM. That's the best you can get. I mean, that's 124% VE trapped. I mean, you're not going to get any better than that. So if you take the same head with 400 CFM that's capable of 900 horsepower, and you could, with the proper cam, lifting the cam an inch 20, turning it 10,000 RPM, you can extract a lot of power out of it. But for a street car with a low lift cam and restrictive manifold and everything else, that 400 CFM is only going to net you 0.55 to 0.56 horsepower per CFM. So just saying that you can attain that much horsepower, it depends on the engine combination, how much power you're going to get.
And before everybody runs out and thinks that they want an inch of lift, let's talk about lift, how it affects power, and at the same time how it can affect reliability. Because there's a definite trade-off.
So what in the 1990s, we had 485 lobes in Pro Stock, and we were using 195 rock arm ratios. And then we got Ford core cams, the 53 millimeters, and we could go to like a 520 lobe with a 185 ratio. Then we got 55 millimeter cams with 545 lobes with 1.8 ratios. Then we got 60 millimeter cams and 65 millimeter cams. So what we've been doing is every time we go up in cam core size, we can go down in duration, up in lift and valve velocity. And by the way, valve speed is power, period. So the faster you can slap it open and the faster you can close it, the less duration and seat timing you need, and the more cylinder pressure you can make at higher engine speeds. That kind of sums it up. So as far as reliability goes, the bigger core cams are able to lift the valve much higher at an increased reliability, an extreme. I mean, I have guys out there that are racing top sportsmen with 1050 gross lift cams, and they go all year on a set of springs. Don't hurt a thing. Turn it at 85, 8800. It's nuts. I mean, we have valve spring technology, push rod, camshaft lobe, valve train geometry, or valve train design overall, thanks to Jessel, because we wouldn't have any engine speed increase in engine speed if it wasn't for Jessel. Now we can have 900 lift cams in a circle track deal that actually live, where that would be unheard of just 10 years ago. So the reliability is directly proportional to the core size of that cam.
That's an interesting way of looking at it right there. Okay. But it makes a lot of sense. A lot less, what was the terminology that Billy Godbold used? A lot less, there was a term he used to describe to valve, but it equated to valve train violence.
We used to brutalize the valve train, and we started learning about loft curves. Our valve spring bill in 99 or 2000, I think, was $85,000 is what our valve spring bill was for the Pro Stock team.
Right.
And that's when the titanium springs came out. Of course, titanium's the worst spring material you could possibly have. And when they send all that crap through the engine and just destroy everything. But what we found is when we put those on the engine lost 20 horse because it killed all the lobe loft. So then we just put then we started brutalizing our way. We just put bigger lobes and bigger rockers because the valve spring could control anything we threw at it right up until the time it broke. So you only got one run on them. So then we really started looking at loft curve. And by the way, a loft curve starts, there's no enough kinetic energy in the valve train to initiate a loft curve under about 8,000 RPM. So with a loft curve, you actually have a variable camshaft. At 8,000 RPM, the cam will actually, of course, launch off of the top of the lobe and then be caught. So you actually get increased lift and increased duration. So at 8,000 RPM, it'll jump up with 5 to 8 more degrees and about 10 to 20 thousandths more lift, and then slowly climb in lift and duration until it goes ape shit crazy at whatever RPM it's going to. At peak torque, you've got plus 5 degrees and about 10, 20 thousandths lift. And at peak power, you've got plus 50 thousandths lift and 12 to 14 degrees. So it's like a variable camshaft, but you're tuning that on the razor's edge. If you're think about what happens. What happens to the torque curve of an engine when you put too big a cam in it, too much duration? It kills it. So if you initiate a loft curve too fast and it jumps up and gains 10 degrees right away, it'll destroy the torque curve. I kind of got off pace there a little bit. But.
No, but that makes good sense. Yeah.
So long story short, bigger cam cores equate to longer, more stability because of the nature of the shape of it, which allows you to use more lift with the same longevity of things as you would with a smaller core and a smaller lobe, basically, right? The bigger cam core you go, the bigger lift you can go before it becomes a problem.
And lifter diameter. Got to throw lifter diameter in there.
Like the Pro Mod camshafts are 68 millimeter now. And they have 695, 700 lobes and 1.7 rocker arm ratios, 1.75 rocker arm ratios. So what that allows you to do is put the lift in the lobe and not in the rocker arm, which is just loads the push rod like crazy. So, and also back like in the 90s, we ran 286 degrees of duration in a 500 cubic inch motor, peaking at 7,500. Now we run 276 degrees of duration and it peaks at 10.5. And that is all because of two reasons: increased valve speed and lift, and the ability to control it. Because as you lift it higher, you can start taking that duration out of the engine. And if you keep those valves on the seat longer, you just build more cylinder pressure.
Now, what about early exhaust valve opening? Shrinking the diameter of the exhaust valve to make room for a larger intake valve, and then opening the exhaust earlier because you're using a smaller exhaust valve.
Yeah. A lot of people forget about the blowdown phase of the engine too. And the intake to exhaust size ratio and the intake to exhaust flow ratio are two separate things, and people get those mixed up all the time. As far as a flow ratio or a size ratio is concerned, it's about 69% of the intake is the breaking point. 70% of the intake is considered normal. But in order, like you said, our whole idea is to take that exhaust valve, shrink it as small as we can get it, shove it over against the bore wall, stick the valve size in there that we need, that will flow the required air that we must have, then shove it as far away from the bore wall as we can until they almost clip. And basically, that's basically what we did. Get that intake as far off the bore wall as possible. And once you get to about 200 thousandths off the bore wall, that valve is pretty much unshrouded. It doesn't see that shrouding on that side anymore.
And this is why you don't run a 4-inch bore or a 4-whatever-inch bore LS3 head on, say, a 3.889 or whatever the 5.7 bore is, or the 5.3 bore. It's because the valves don't even clear the cylinder walls.
Yeah, and if you put too big of a valve in an engine, it's more detrimental. It's far more detrimental than putting small of a valve. Because when you put the correct size valve in there, your air speeds, your flow potential, and everything is matched to the engine. Now, if you try to push that and say, okay, I'm just going to stick the biggest valve in there, get the most airflow I can, and try to get the most air RPM, the most engine speed I can. Basically, when you start increasing that valve size, the discharge coefficient starts dropping. The efficiency of that port nosedives at a certain point. So even though you got that valve area, and even though you did get an incremental more flow, you actually lost efficiency, and you'll never reach that valve's potential. You won't even get close to it because you just killed it about 10%. So, and what I mean by that is, if you put too big a valve in there, you will shroud it off, and it will flow less from at 200, 300, 400, 500, 600 lift. And then once it's above 0.35 lift to diameter ratio, it'll start seeing itself as unshrouded. At that point, the valve almost becomes, it's like it's out of the way. The port almost doesn't see it. So you'll get a huge spike in top end flow numbers, and you'll think that you actually made a gain when the average area under the curve is actually deplorable. So if you can't get it started, if you can't get that intake charge started instantly, you can't make it up later in the cycle. It's done. It's over. You just killed VE. So when you kill the low end efficiency of the port, you can't get it going. And if you can't get it going, you kill the inertia effect behind it, and your VE suffers. Next question.
Who else has questions? Go ahead.
Well, I can't see the Facebook feed or the YouTube feed, so I'm hoping that maybe some of you guys are watching that.
I'm having issues this evening as well. I don't have enough network bandwidth. I don't know what's going on.
Does the high lift, low duration apply to an overhead cam motor as well as compared to just a push rod motor?
That's a trick question. That's kind of a different world, because you can't get valve speed in an overhead valve engine, that's why they're really difficult to create a lot of torque with those engines, because the lack of valve speed, you just have to make up. Like in the old days, you just threw duration at it, hung the valve open longer if you wanted to increase engine speed. Well, that's not the correct path to do. But in overhead valve engines, that's exactly what they do. So when you have a push rod engine with a rocker arm ratio, you can increase valve speed dramatically. Let's take the Chevy RRL project that I worked on. The original cylinder heads did not have a rocker follower. They were just a bucket and cam lobe system. And when they went to a rocker, a 1.2.25 rocker arm ratio on that, they increased VE 5%. It was like stupid. It was amazing. And actually duration shrank by 10 degrees both sides.
Wow. Wow. Okay. Keep going, Evans. You got any other questions?
Oh, it's the Pro Stock bikes. It's for Schumacher when Angel and Brown were with them. And those things were amazing because the lobe is shaped like this. I mean, it comes to a point. It's the 700 lobe. And in order to get valve speed, they took a flat bucket and they made an arc on it. So what that does is, so you have a lobe come in and you actually have an acceleration of the valve with the spherical top. That's what they had to do to get valve speed in the motor so they could make power.
So what do you tell someone when they're looking for a cylinder head that isn't for a heads-up racing class? Let's say a guy who's looking for a cylinder head for a street engine. What he's wants to buy a set of heads for his LS3 powered or LS powered drag car, and he's going to put a supercharger on it. What should he buy for heads? What's he looking for?
It depends on what his power goal is. And well, it depends on what he's trying to get, what he's trying to attain. I mean, if he wants anything over 800 horsepower, I'd say go to aftermarket cylinder heads that are thicker. As far as the port designs, chamber layout, and everything else, I mean, the LS3, LS7 heads are plenty capable of making 1,000 horsepower with a turbo pretty easily. So basically, you just want the strength. You want the structural rigidity. You want a 356, a good alloy. So it won't distort. The decks won't distort. The seats won't move around, and it's actually repairable if you do break it. That's what I always say. But if the guy wants 600 horsepower, 650 horsepower with a supercharger, I say, yeah, go ahead and use the stock heads. It's no problem. So it depends on what he's doing. It depends on his power goal.
How about this question from Victor Don on Facebook? Do you guys see that, or am I the only one looking at Facebook?
No, I see it. I can't get my message thing is going real weird right now.
Yeah, Evan's posted in the chat as well, but let me scroll back and find it.
Do you have a rule of thumb for intake port speed versus angle of approach? 260 feet per second on an SPC versus 300 plus on a four valve dirt bike engine.
That's two different worlds, because 4 valves function off of average airspeed, and 2 valve heads work off of both peak and average airspeed. So that's completely two different scenarios. As far as a 2 valve is concerned, the average overall airspeed in the intake tract is 245 to 265 feet per second. And in a 4 valve, it can be up to 350 feet per second. But it depends on the engine, its intended use, the power goal, and a lot of other factors. There's no packed airspeed I can tell you that's going to work in all cases, but I will tell you that the average airspeed in the 2 valve is almost always 265, 300 peak through the peak as far as the secondary choke, the pushrod area, and as high as you can get it with the most flow you can get through the throat.
Could you spend a minute on talking about this 2 valve versus 4 valve theory? Because obviously there's a lot of religion around that, and yet most of the engines in most of the world are overhead cam 4 valves. But we've got some, the LS series, obviously, and then the new 7.3 Ford Super Duty engine that are going back to 2 valve pushrod. Can you kind of go into, why those two architectures persist and what the differences are, and why maybe we shouldn't be trying to compare them, or maybe we should?
I can give you my opinion on that. Like we have a couple of Godzilla engines in the shop right now. I've got a prototype cylinder head, all digitized, ready to do. We're going to go on the dyno with it. Why would they go back to the pushrod versus the overhead valve? It's more of an engine speed issue than anything else, in my opinion, because a 4 valve has to turn higher to make power than a 2 valve does. A 2 valve makes brute low end torque. They can fill the cylinder at a lower engine speed, and that for a truck or a passenger car is superior to something that's got to turn another 1,000, 1,500 RPM over its lifespan. Basically, it's the torque curve. The 2 valve makes a very broad torque curve over a wide range at a low engine speed. And I think that is why they did it.
Now, does that have to do more with when you go to 2 intake valves, the intake port becomes so large cross-sectionally that you've got low port velocity at low speed?
It gets very, very difficult to manage with the 2 valve. Again, because if you have 2 individuals, like an IRL deal or sometimes some of the Formula One stuff, if you have 1 port for every valve, it's simple. But when you merge those 2 valves into a single port, that gets a little bit difficult. Then you have to start making compromises. And that goes for any cylinder head or any engine combination. It's always the best set of compromise. And with a 4 valve, yeah, you have to sacrifice airspeed, especially in the bowl area around there, in order to get the flow potential up to make more power. But you can make that up with the average airspeed upstream, not by choking it down more, but by taking taper out or manipulating it, or the runners, or something else like that.
Keith Starner is wondering, is there a calculation to figure out valve speed? And if you could figure out valve speed, what are actual good or bad numbers?
Lobe intensity, or the actual rate of opening or rate of change of velocity on the opening ramp, is a tuning variable in camshaft design. But as far as a specification or a max valve velocity, I've never seen that put to paper. I don't think anyone can do that, because you're dealing with too many other variables here. You're dealing with the valve weight, the spring weight, you're dealing with all the kinetic energies in there. So on that side of the cam, that's a different tuning regime over there. Camshaft, from the camshaft to that. And we know that we can lift it so fast with that lobe, and then we go and play with the rocker and the push rods and everything else to try to make that work. So there are limits. At least today there are limits until we get better valve spring, better metallurgy, better material science, and everything else. I mean, if you look at there's only 3 classes for unlimited, normally aspirated drag racing, and that's Australian Pro Stock, NHRA Pro Stock, and Comp Eliminator.
Now, you were working on a head for Australian Pro Stock for a while, weren't you?
Yeah, it's been in production now for 8 years. The Profiler Airstrike cylinder head is the basis for that cylinder head. And then you take the Airstrike and you put the valve train on it that should be on it, and you do some other things, move the valves, clock them a little bit, and you have an Australian Pro Stock head. Now, the 4.4 bore space small block Chevy will produce about 1,065 horse at about right at 10,000. But if you look at the Mopar with its wider bore spacing, it can get more valve area in that thing. I mean, that one engine that Bob Book did for Australian Pro Stock, when he told me that it made 3 horse per cubic inch, of course I take everything with a grain of salt there, and because nobody's done that. Nobody has hit 3 horsepower per cubic inch, but he did it. He actually did it. And it ran that way too. The mile an hour showed it.
How close are you to 3 with the 500-inch stuff?
2.96, 2.98, real close.
You're knocking on it.
Well, it was there until they knocked the RPMs back down.
Right.
So,
any other questions?
I apologize if this has already been asked. I mean, I have my opinion on it, but what do you think of the dimple port stuff on the intakes and on the intake ports themselves?
it looks cool. In some scenarios, in some situations, this is where people get false data, because they'll take a port that is way too slow, way too big, and they'll do that and rough it up, and it makes more power, and they think, oh, the dimpling did it. Well, yeah, it did in a way, but if you shrink the damn port back down, it would make even more power, and you wouldn't need to dimple it. And dimples, depending on how they're done, will actually pull and deatomize the air fuel mixture. It'll actually, everywhere there's a dimple, it will suck that fuel out, and it'll sit there and spin.
Because if there's any velocity over it, it'll be a depression, right? I mean, it just seems to make common sense.
Yeah.
Yeah, and dimpling is different than dimpling is different than texturing. It's two different things.
A texture is an uneven surface, so it's got jagged edge sticking out, so it makes the boundary layer jump away from that wall. It makes it twice as wide. So, and then, yeah, there's negative depressions in there, but it's so uneven that the fuel can't grasp the wall. But if you make everything even, all those dimples the same size, you've just got a vacuum for the fuel. And some people think, well, yeah, that makes more power. But again, they're doing it in ports where it will show up because the ports aren't designed properly in the first place.
So what you're saying is, unless you're in a cylinder head tossing competition, leave the dimple ports out.
Unless you're trying to band-aid a situation, leave them out. If you have a port that's too big, its airspeed is too low, it can't carry the air fuel mixture. So the deatomization rate is going to be enormous. So if you make it really, really super rough, even though you get some more deatomization, it will actually help reintroduce the fuel back into the airstream some. So it's pulling it out, but it is still reintroducing it. So you're band-aiding the situation.
That makes good sense. What else?
I've seen a bunch of people ask about the thoughts on, I believe they say 3-valve. 3-valve SBC heads and just 3-valve in general. When we were talking the 2-valve versus 3-valve versus 4-valve, all that stuff.
2-valve, 3-valve. Well, I will say this: the number one mistake people make with 4-valve engines is they over-exhaust them. And people do the same thing on 2-valve engines. Point in case, a big block Chevy cylinder head, you can take any conventional cylinder head that you buy, take that 1.880 valve out on the exhaust, turn it down to a 1.850, and it will immediately gain low-end torque and mid-range power. It actually breathes so much better with a smaller exhaust valve. And we don't need exhaust valve sizes as big as most people think. Pro stock can produce almost 1,200 horsepower at almost 11,000 RPM with a 1/600 diameter exhaust valve. We don't need it because with the smaller exhaust valve, you can accentuate the blowdown phase, open it early, which that blowdown phase, you're opening it against higher cylinder pressure. So the hit on the exhaust pipe is harder. So you actually get that later on in the cycle when the piston, you're opening it up. Okay, point in case, a top Pro Mod engine. A Pro Mod engine has a 6-inch stroke, and we're opening the exhaust valve when it's 1 inch down the bore. We're initiating a huge blowdown. So when the piston turns around at bottom dead center and the exhaust valve is coming shut and it's trying to shove exhaust, that's the exhaust phase. When it's actually trying to exhaust, it has less to exhaust because you've accentuated the blowdown phase and you've got most of it out during the blowdown. So you don't have to exhaust it later, which reduces pumping losses and increases power. But in order to have enough time for the gas exchange process, we had to pop it off only 1 inch down the bore, which is why you see these huge blue flames coming out in things. If you didn't open it and accentuate the blowdown phase in order to evac the cylinder, you would contaminate the next incoming charge with heat and it will go bang instantly.
Right. Okay.
So
will it actually auto ignite from that heat, from that exhaust temperature?
Instantaneously.
Really? Okay.
And it will literally shove shockwave diamonds right out. I have had pictures of when the engines detonate, it will have a beautiful Taylor line and about 3 shockwave cones coming right out of that header. Wow. It's amazing.
Because of that, the burn, the combustion front is absolutely hauling ass at that point, right? I mean, is that, yeah.
Nitrous is extremely difficult to control after a certain point.
Right.
Really, really hard to.
That's why all the piston manufacturers love the nitrous guys so much.
We do, it's just the opposite of an NA engine. We do everything we possibly can to slow the burn down in a nitrous engine. Big, huge, deep chambers with the plugs as close to the center as you can, which you always try to do that anyway. And big domes. You'll actually make the chamber bigger so you can get the dome bigger to slow everything down. It's just the opposite of an NA engine. Now, back to the 4-valve question you asked as far as the exhaust and intake is concerned. 3-valve versus 2-valve. So say you have a 4-valve engine, like the 2JZ heads that I did for Titan, when we were working with those, I mean, those engines would make 2,200 horsepower out of 181 cubes. And the exhaust ports were stock exhaust size, stock throat, stock.
Wow.
Only thing I did was just go in there and streamline it. That was it. So I kept the velocity extremely high, which instantly spools the turbo better. And the efficiency of the turbo in that system goes up dramatically when you do that. So you put a big exhaust valve in it. Now you killed the speed. You have more airflow potential, but do you need it? 90% of the time you don't. It's just a waste. You're killing airspeed. You're not able, it kills the efficiency of the turbo and everything else. Even on normally aspirated engines, most 4 valves that I work with, I do not change the exhaust valve size, only the intake. So on a 3 valve, Is a 3-valve better than a 4-valve? I can't say. I don't think so. You don't have that instantaneous area of hit. You don't have the variability of camshaft tuning, I would think, on a 3-valve. But would it make as much power? Yeah, it'll make as much horsepower with a single exhaust valve and 2 intakes. It's just different design criteria for the cam and valve train and everything else. You're muted.
Oh, sorry. Who has questions for Darin? My bad. Anybody else? No, I can't see Facebook or YouTube, so I was kind of hoping that
trying to scroll through the Facebook's doing the whole I can only see so much, and I swear there's stuff I saw that's missing now.
Right. Thanks, Facebook. What about YouTube? Can you see YouTube?
I can. It's being a little crappy for me tonight.
Yeah, every time I've opened YouTube up here, it kills my network. I don't know what's going on.
Going back to that push rod deal, the valve train resonance destroying the power curve.
Yes.
One thing, it's kind of funny that through the course of experience, it's like I started the AIST, the Advanced Induction System training deal, to basically show people what I do for a living and how I do it. So they have a better understanding when they come in here and ask for something. And they're also able to make better judgment, better decisions after they go through that course.
That makes a lot of sense. Yes.
I mean, I can tell somebody exactly how I do it, show them how I do it, give them all the data I've collected over the last 35 years. And could they do it? No, because they don't have the underlying basis of experience to draw from. And that push rod deal is a prime example because I've seen it 50 times in my life over the last 30 years. And the reason I put my finger on it is he said that the valve train, the locks and the retainers came apart easily. Now, when you have a system in float, a valve train system that is erratic or going completely crazy, it will lock that valve and those locks together, and you almost can't get them off. And some of the early days in Pro Stock, we used to have this big thing with a 5-pound sledge to bust them loose because they would lock up so hard. Now, that's an indicator of float or going erratic at the top of the gear change. So when he told me they fell apart, I knew instantly that the chances of it being the push rod were extremely high because that it doesn't transfer as much energy into the spring to lock that system up right there. So just knowing that it does that doesn't actually point you in the direction of fixing it. I hope that made sense.
Yeah, I think so. I've seen a few guys ask this, and this is might open up another can of worms because anytime this comes up, everyone here hates on it. But thoughts on direct injection, and I guess more about how would that impact head and port design, et cetera, on a direct injection, kind of going back to how we were talking about.
You don't have to look any further than the 5.3 and the 6.4 LT, LT1, and LT4 heads. If you notice, they went down in intake size to a 2.125 intake from an LS7's 2.200. Why'd they do that? Because there's no fuel. The charge density went way down. So now in a dry flow system, in a direct injected system, it's injected in the combustion chamber. So it's not in the runner. So now to get the airspeed up in a dry flow system, you can actually run it faster than you can with fuel. So you shrink the valve down, and that way you can get the airspeed in the whole runner perfect for the engine combination. And I will say this: direct injected engines suck. I hate them because the power potential is low. You can't make a lot of power with them because your injector spray time, especially, the injector, any low profile direct injector has a spray time of about like that, where some of the 4 valves have them here, and its spray time is like a standard injector, standard port injector. But the LT engines, I dislike them greatly. They have about 850 to 900 horsepower potential with the direct injector. And after that, you have to put an upstream port injector in it to get any more power out of it. And some of these 1,200 horsepower LT4s that are out there right now with ported superchargers, cammed up and everything else, have to have more than half of that power made with the injector in the runner. As a matter of fact, if the runner injector goes out, the engine will just die. It's so lean, it can't even run. So I dislike direct injected engines for that reason. And the other engine is valve coke. I see so many of these cylinder heads. I was doing a road race engine for a guy that owns a Chevy Cruze. So he brought this little 4-valve direct injected head in, and I have pictures of it on my Facebook. The tulip valve was like at a 50-degree angle, and it shut almost the entire port off. The valve was so coked up. That engine had 12,000 miles on it.
Yep, that's about right. That's what we saw in OEM testing. I've got a walnut blast our BMW every 20,000.
Wow.
And they 100 times worse with exhaust gas recirculation by retarding the cam 20 and 30 degrees, that's the first thing I do with any new car I go into. I get HP tuners and I frickin' take that out, because I did that on my Chevy Cruze, as a matter of fact.
Oh, careful now. EPA might be listening.
So, I mean,
Okay.
injection, awesome in the case of low-end torque, mid-range power, absolutely fabulous. Throttle response,
EPA drives. Yeah.
but not for power.
No, it's emissions. That was the biggest thing, emissions and fuel economy. And
Yeah.
that's 100% from word at the OEM why we started using it.
Sure.
And it
But
made
not
my life
carbon credits.
miserable.
They didn't take credit. They didn't say anything about carbon credits, though, did they, at the OEM, even though a big part of it is
I
for
mean,
carbon credits.
it would be, I wish I could remember how that was worded. It was a very political wording. I'll leave it at that. I
I'm
think
sure,
my
but
NDAs are up. I don't think I can get in trouble for anything anymore.
Riddle me. This is something I don't understand. I understand the reasoning of why the OEMs did it for EPA standards and efficiency, burn efficiency. But if the valve cokes up after 12,000 miles and shuts the port off, what's that do to the efficiency?
Oh yeah. So I will say that's one reason we didn't, when I was at Honda, we waited so long to go DI, and we still had issues with it. And I could tell some stories of when we took apart BMWs, and then some of our marketing and higher ups that weren't engineering, like, yeah, let's do a hot V. And I'm like, seriously? No, like, you took these engines apart that have serious coking problems, and BMW went to factory water injection just to fix oil coking.
Really?
Yeah, they've got some of their M5s and shit, I should have checked the M4 I tuned today. I don't remember if it had it or not. Some of those engines started putting on factory water injection, and it wasn't. Everyone's like, "Oh, this is awesome! It's race cars." Like, no, it's because they don't want to do the maintenance anymore, and they got tired of warrantying parts because they were failing just due to oil coking.
That's some interesting stuff right there. That because I know from the GM stuff. I visit a GM dealer that also has a racing engine group and a dyno facility down in Texas, and they had a couple hundred bays, and they were telling me, man, the warranty statistics are scary on some of these DI engines. Basically all of them need to come in for get walnut shells blasted down their throats. And cleaned out, and some of them disassembled, before like 25, 30, 35,000 miles, well.
Yeah, I mean, my wife's car is probably 8,000 miles overdue for walnut blasting, so I'll get some nice pictures of that when it's time.
So,
Think about
I have never had the intake off or the head off of my Audi, and there's 164,000 on it right now. So
Let's
that could be
just say
some.
Mark doesn't have a carbon buildup problem.
There could be some interesting photos there.
think
Audi,
about
but gives it the Italian on the way home from work every day.
think about what they did there. They just saddled your ass with a $1,200 carbon tax, because now you got to clean the damn thing out.
So, Darin, going back to valve speed, and this is going to take a little clarification because I think he's slightly confused here. To verify with the overhead valve to increase the valve speed, I would increase the duration. 2.3 turbo SVO head specific. That's how he understood it.
Okay. No, valve speed is increased with maintaining the same duration and increasing lift, or decreasing duration with the same lift, or decreasing duration and increasing lift. The more duration you put on the camshaft, the slower the overall action is. So basically what you're doing is, let's say you have a 500 lift camshaft with 260 degrees of duration, and then you take that to 240 degrees of duration, you've just achieved that in less time. So it's got to be faster.
So isn't that why all these EMC engines were running 2-to-1 rocker or 2.2-to-1 rocker arm ratios? Just kind of cram all that into the event to get the valve
that and
fast as possible within the envelope, and given the RPM range.
Yeah, the RPM range is so low that you can't have any duration. So, and you still need the lift to make the power.
So basically what you're doing, let's take a scenario like the old days in unlimited engine, like a Pro Stock engine, when you had 286 degrees of duration and 850 lift. And now you have 276 with 100 and 150 gross lift. Think about it, you're actually lifting it higher in less time. Think how much faster that has to be to do that. Now, what you're also doing is you're maintaining the same area under the curve. That's important, because if you take duration out and don't add lift, you're decreasing the area under the curve. But if you add lift back in and you trace out that area under the curve, it will be at least the same or more. At least that's the goal.
Yeah, so the big problem that we had with the Pontiac was one of the rules that the Engine Masters Committee had was it had to be a stock diameter cam core. And that, of course, was a huge disadvantage when you've got LSs, Gen 3 Hemis, other big block Fords, other engines with large diameter cam cores, when the rule says it has to be a stock diameter cam core, because I think the stock Pontiac is one of the smallest cam cores I've ever seen. So what we ended up doing is we worked with Tom Vigu, and we developed some lobes that would work with short duration with 2.1 rockers. And that was simply because of the diameter of the cam core. We could not get out of the lobes what we needed to with the cam core, so we did it with rocker arm ratio instead. And that's kind of what Darin was talking about, the progression of the race motors that he worked with. Pro Stock is now at a 1.7 rocker, but that's because they have a 68 millimeter cam core. If I remember the numbers correctly.
We go down rocker arm. We want to go down in rocker arm ratio. And the reason, if you look at a high ratio rocker with a high pull and moment of inertia, will take that rocker arm and the push rod and bend that sucker and then store that energy late in the cycle and release it. So the lower, and actually the initial jerk on the system is much higher with a high ratio. So if you lower that ratio down, you lower the load on the push rod, the initial hit isn't as hard, and it's a lot easier to control at high engine speeds. I mean, when you're turning, 363 cubes, 11,200 RPM, and dropping it back to no lower than 9,600, you can't run anything over a 1:7 ratio. You can't control it. Even with a 60 millimeter cam. As a, by the way, the new Godzilla Ford has a 60 millimeter cam and 300 install height on the spring.
Really?
Lots of room. I mean, these are going to be 950 horsepower engines like that. Easy.
Awesome.
But going back to finish what I was going to say to Bill, we ended up at 243 degrees of duration at 50, but we were showing 840 something thousandths at the valve, with deflection and everything. So that obviously is fairly aggressive.
Yes,
you would say that.
Go ahead.
Back when my stepfather, Kip Martin, was grinding his own cams for Superstock, he raced a 352 FE with a 64 Ford Galaxy 500 XL, and he grinded his own cams, but he would take a stock cam and keep grinding the lobe down the base circle and making it smaller and smaller and smaller, because what that does is it makes it more radical. It makes it nastier and nastier and nastier. the more you shrink that base circle. And at a certain point, it would become uncontrollable. But up to the point where you could shrink it, and gain valve speed and get that valve speed up, the initial hit, it would keep increasing power. So that kind of gives you an indication of how touchy that is.
You're going to like this question, Darin, because it plays into your new position, I believe. But if you were building a 450 cubic inch LS engine, normally aspirated, seeking 1,000 horsepower, which head would you start with?
Repeat that, please.
If you were building a 450 cubic inch LS engine, naturally aspirated, and you're looking for 1,000 horse out of it, which cylinder head would you start with?
NA or turbocharged?
NA.
Okay, well, that's going to dictate the engine speed right there. 1,000 horse out of 450. Yeah, you're going to turn that 1,000 horse. You need 465 CFM of airflow. And at the proper hour speed, that would be about a 2250 or 2260 inlet valve. So, I mean, you're going to need a really good aftermarket cylinder head.
Yeah, and that's what the question is which head would you pick?
And turn at 9,000 RPM, I'm guessing.
Well, of course, I would use a Moses LS or the masthead at Moses. Or if you wanted to go extreme, you could use Dart LS. Now, the Dart LS is a whole new animal because that thing is an Australian Pro Stock head on an LS engine. I mean, that thing is made for max power. That's something that's got to, a 450 could make 1,200 easily at 10 grand. Most people don't need that. I mean, most people don't need to put that extent. For 1,000 horsepower, you could get a Moses head. You could probably do it with a straight jacket head. There are a multitude of heads out there that would fit that bill. Being NA, of course, you'd need something that you could put a good Jessel or T&D valve train on. So yeah, I guess I'd pick the Moses overall.
So we never did really cover your background in depth, Darin, but you were at Rear Morrison for a long time, and then you went to Profiler and did a bunch of development work, and then you went back to Rear, and now you're at
Mast Motorsports.
Mast. And what prompted you to move to Mast? What was the deciding factor there? What held your interest where you wanted to go to that to try something new?
Actually, I went to Profiler for one simple reason. I wanted to learn everything there was about the foundry process and about producing cylinder heads from the ground up. And that was the only way to do it, was just go to work there and learn it. So after I got that out of my system, I went back to Rears. I think I have a total of about 21 years there at Rears. And then when this Mast deal came about, it offered me the opportunity to work not only with a professional team, we don't have any PEs on staff, but we have 2 engineers. Horace is an engineer himself. I have the ability to work with people with such an amazing amount of support that I can do 10 times what I did at Rares within a year, as far as designing new products. They don't pull any punches. If you need a cylinder head, they just design it and go have it cast. They don't mess around. It allows me the opportunity to work on a multitude of different induction system designs, where at Rares, it would be drag racing, truck and tractor pulling, pro mod, pro stock stuff. I'm doing diesel heads for the last 3 weeks. That's fun because that's about managing mixture motion and flow potential, and mixture motion takes precedence over everything. So that's a different design criteria, a different world. So that's a challenge. That's fun to me. Of course, I don't care if it's a Briggs and Stratton or a horseless carriage. I'll work on it if it's a challenge. And the more the rules dictate that you can't do things, that's where I like more than anything else. Like the X275 class, I wish I had some pictures of that thing. They allow you welding epoxy on the manifold. So I take a Profiler manifold that's cast, chop it, build a sheet metal plenum for it, weld the top back on, blast it, and go over it, and you can't tell I even touched it. It looks dead ass bone stock. I like doing that. And it's not that I'm trying to cheat. I'm trying to keep it out of tech's eyes. Because if you look at a cast manifold that's got a sheet metal plenum on it, that's extensively modified. And they're probably going to go, hey, listen, we need to make a rule against that. Don't do that. So I'm going to be within the rule book, but I'm not going to indicate what I'm doing to everybody else. That's fun. So I just have a chance to do so much more with a really professional team. And that's why I went with Mast.
Now, when you were at Profiler, you are the driving force behind what we now have as the Sniper and the Sniper Junior intake for the big block Chevy, correct?
Yeah, and the Hitman and the Tolerant.
I'd like to thank you for that, because you went and gave us an as-cast off-the-shelf manifold that runs with what we used to spend $2,000 to get.
And that's exactly why I did it. I did it because I got tired of spending $2,000 in welding and fabrication on a Dart manifold in order to extract the power. And you think about the Dart manifold in its day, when you had 18 degrees, 14 degrees square port, slow ass heads that were inefficient as hell, that manifold worked perfectly. Now, once we got with bigger cams, more lift, more efficient ports, better combustion chamber design, higher engine speeds, that manifold was no longer sufficient. So I designed the Hitman. And I always say that if you took the Hitman back to 1990, it wouldn't run at all. It would be a dog. It would be a complete disaster because we didn't have the cams, the lift, the efficiency or anything else to utilize that manifold. And then after, I think it was 8 to 10 years, Edelbrock came out with their manifold, which is even a little bit better than that. They make the same power. Nobody wanted them. It's like the Dart 245 as cast versus the 245 or 255 CNC heads from Dart, the conventional big block Chevy heads. They make the same power, but the as cast 245 is $800 cheaper, but the CNC versions outsell them 10 to 1 because people think that ports need to be pretty to work, and it's ridiculous. So that's why you don't see as cast ports that much anymore, because people just didn't want them.
See,
that may be the single most important thing that was said on this the entire podcast tonight, is letting people understand that port finish is not all about having everything polished to a fairly well.
The more you all know, the stickers and powder coat adds 10 horsepower automatically.
So that said, we had a picture that was in the ad for tonight's show, Darin, that showed this beautifully smooth pocket area of, no valves looking into the pockets of the ports. And you had talked earlier about, a 30 grit finish at the runner entry up in the manifold. So what does that progression look like? Because we've now, explained to everyone that dimples are a crutch, but what does happen to that finish as it makes its way from the runner entrance in the manifold all the way down to the short turn?
I can explain that very simply. When you have a runner and it has taper in it, the airspeed is lower at the plenum than it is at the choke point down in the port. So the air has to accelerate. So with the airspeed being low, the air fuel mixture can separate quite easily. So you have to take that boundary layer and move it off of the wall as far as you can to try to help suspend the air fuel mixture within the middle of that runner. So if you make it smooth, it will adhere. So where the airspeed is the lowest, it's the roughest. Where the airspeed is the fastest, it's the smoothest. And also, if you take a properly designed port with a proper wall texture that's atomizing perfectly, let's say the port is 90% efficient, about as good as you can do, and you polish that port on, say, a comp engine or a pro stock engine, it'll lift land like that. Instant. Detonate the engine. Because I've seen this so many times. The boundary layer just goes right against the wall, and so does the fuel. So now all the fuel goes onto the wall, and you get a lean hit in the combustion chamber, and bang, off it goes. Smooth walls make an engine or a chamber detonation sensitive.
Now, what about a smooth chamber or a polished chamber?
Well, you can polish the chamber all you want, but it ain't gonna do you any good. And you can have it at 60 grit and it'll run the same. Why is that? Well, actually polishing can be detrimental because if you have a little bit, let's say your oil ring is a little bit loose, that oil will just sit on the top of the piston and it won't burn off on a polished piston. Now, on something, a piston, let's say has a 60 grit finish, it'll carbon up immediately. And carbon is a pretty good insulator on its own. So if you polish it versus not polish it, coat it versus not coat it, the power difference is infinitesimally small. There is, in some cases, a difference, but it's very little and almost undetectable in most cases. So polishing the combustion chamber and the piston is not necessarily detrimental, but it's not really advantageous either. I mean, I've been through coatings and polishing and not polishing and I've been through that so many times. And I will talk about coatings. And it depends on the coating you use too. Are coatings worth power? Yes, a little bit. On bearings, camshafts, stuff like that, friction, anti-friction coatings on skirts, yeah, that's instant power, that helps. Coating a combustion chamber and a piston, however, is usually a waste of time and money. And I'm gonna know the coating manufacturers are gonna kill me for this. But you can also coat a piston and change the thermodynamic properties at the top of that piston and lose ring seal just doing that. Because on the exhaust side and the intake of the piston, it expands at different rates. Well, that's baked into the design, the barrel, the taper, and everything else of that piston. When you put a coating on the top, and I'm not talking all coatings, just some, it will actually change the thermodynamic properties, the top of that piston, and it will expand and contract differently. And you'll actually lose ring seal and take the skirts out faster. So you have to be careful with that.
So you brought up piston, expansion and ring seal. I'd like to talk about one of my favorite subjects, crevice volume. Darin, how do you address crevice volume?
Make it as small as possible.
You may want to define crevice volume for the audience before we talk about making it small as possible.
Right on.
Crevice volume is top of the piston, and let's say your ring is 300 down. The volume from the bore to that ring right there is the crevice volume. Is that the volume you're speaking of?
Yep. And that maybe the crevices on the outer edge of the head, or anything where you don't have good combustion, but mainly the area above the ring. Yes.
So in unlimited engines, the top ring is about 50 thousandths down from the top of the piston. It's only 26 thousandths thick and about 140 radial. The reason we go to those real small rings is they're gas operated rings. There's very little wall friction, very little radial tension on that ring. And we're able to, with the valve relief, and you've only got, that much of the valve relief, you can actually raise the ring higher than the valve relief because it has such a thin radial. And that reduces that crevice volume around there. Now, the crevice volume itself, if you're looking at the volume of one cylinder, that's not a large percentage. It's like 1/1000th of 1%. But at TDC under compression, that crevice volume accounts for, I think, 1.3% of the total air fuel mixture. And if you move it down, that'll go to 2 and 3% real quick. So by moving the top ring up and reducing that, you get 1 to 2% more air fuel mixture that you can actually burn and create power with. Also, around the edge of the piston, around that crevice volume, the squish quench area, I could talk a long time on that. That's the point. You can get in what they call in-gas detonation. If your plug is way too far away, like an old Buick head or something, the spark plug's all the way instead of moved as close to bore center as possible, the flame front propagates 360, and by the time it gets halfway or 3/4 of the way away from that plug, it is pre-compressed the air fuel mixture on the other side, and if it's lean, it goes bang. So that's something to consider too. Question?
Well, as long as we're stirring up the pot, let's see here. How am I going to phrase this? Rod to stroke ratio.
Jesus, here we go.
I love. Rear Morrison did some tests on some NASCAR engines where they varied the rod ratio. They varied the rod an inch. He tried to keep everything the same. And of course, you could lay those power curves over and you couldn't tell which engine was which. Because in a certain range of 1.6 to 1.75 rod ratio, you're not going to see a difference. Once you get above 2 to 1, you get what's called port pressure lag. And that's impossible to manage. People keep thinking, well, if you have a high rod ratio, I'm going to have more dwell at top dead center during the power stroke. And that's correct. But you also have more dwell during the intake stroke. So you have a lag. So you can't get the whole system moving as fast as a faster piston speed. So that is something in like little 265, 300 cubic inch motors. That's why they go to 8-inch decks or 8.5-inch decks, is to get that rod ratio up into the 1.75, 1.85 ratio. And that anywhere from 1.6 to 1.85 is going to make the same power. Anything below 1.6 and 1.5, it gets harder on the skirts, and your rings go away quicker and your skirts go away quicker. And it is a little detrimental power because it increases the friction power. So you're going to lose a little bit there, but it's not a huge significant amount. And the Pro mods right now are 1.31 rod ratios turning 8,500 RPM. So there's no magic there. And this is where people make a huge mistake, is they get this idea in their head that they need some preconceived rod ratio, and they're willing to completely screw the piston design in order to achieve it, because you want a piston design with the pin as high as you can, so you don't have a top heavy piston and it's reactive and it's not loading the skirt hard. So if you have this super tall deck and you want to achieve this rod ratio and you just put a tall piston on it, well, that just destroys the whole system. So the rod ratio,
like a 440 Mopar.
Yeah, good point. Yeah. I mean, I always say that you design the piston properly and you get the stroke and the bore that you need to attain whatever you're trying to do. And then whatever connects those two is the rod ratio you live with.
What about, I got my 6-liter and my 6-liter LS, I'm going to de-stroke it so I can turn some RPM when we're talking about a 3.662-inch stroke.
As far as piston speed goes, you're going to have to make a pretty big change to change the piston speed. There's no substitute for cubic inches, especially when it comes to your pocketbook. You can make more power at a lower RPM range with more displacement. If you're going to whip out the RPM game, you better whip out your wallet and open it wide, because it takes a lot of money to turn these things up. I mean, you're talking about you can build a big block Chevy 632 that makes 1,200 horsepower for $28,000 or less than that, $26,000. And if you want to make 1,200 horsepower with a 400 cubic inch small block, that's $120,000. So,
holy crap. Yeah, that's an interesting perspective. No one's ever laid it out like that before. That's awesome. Wow.
Well, I think the big thing too is, like, I see so many guys saying, "Oh, I want to turn all this RPM," and even in my case, I get more guys that's more justifiable. But half the guys, I'm like, "Why? Why do you need RPM? You know, what is it to make power?" And the few times it's come across is sometimes in drifting and sometimes in road racing when we have a gear limitation. We need the wheel speed coming into a corner or something like that. But even then, there's 99% of the time a better way to fix it that is way cheaper.
Engine speed is what you're stuck with when you can't increase displacement and you have to increase power, because that's all you got. Yeah, it's definitely not the go-to thing.
For sure. expensive.
Those are just a couple of things that fly around the internet, and I thought I'd address them.
What do you think?
I just wanted to add to the topic of small engine versus big block cubic inches, and just say that just because it can be cheaper to make a big block doesn't mean you're going to spend less. Because I started off with mine as a thought of, I'll sell the smaller LS engine and jump up to a big block and not have to spend a whole lot of extra money. But when it came down to it, I started going, well, I really want this extra reliability, and I want it to be beefed up and beefy and be able to make a lot of power if I ever want to without the risk of hurting it. Like on a whim, I decide at the track that, what the hell, let's put 30 PSI in it and send it. I want it to be able to live versus building something that might only be good for 6 to 8 PSI or naturally aspirated even, which I could do fairly budget. I could go to a junkyard and pick up a big block and do it for dirt cheap, naturally aspirated, spin it 5,500 RPM and make a ton of power still. But when I decided that I might want to just put the full Monty into it and send the thing, it became increasingly expensive because now I started looking at, okay, I need a good block. Oh, now that I have a good block, what's the next weak point? Oh, yeah, I don't want to put crappy pistons and crappy crank in it. I need to put something good in it. Oh, now I need to start thinking about, while I'm getting this block, I probably should put in the bigger lifters. So now I need to bore out the lifter bores to the 937 size. And, now it becomes, I better put in a decent cam core. And now, it just slowly adds up. So don't think that just because you're adding cubic inches, it's cheaper, because in the end, you may end up spending just as much on either version of the engine, like I have.
To be fair, we could take a lawnmower and do the same thing with that project.
Yes.
This is how I wound up with a $15,000 cheap road race Miata I got for free.
Sorry.
Hey, Brian, is your Miata, is that V8 powered or is that still a Miata power?
It's still Miata power. It's been threatened with many other engines. When it blew up the third engine or the second engine, I put the third engine, it was threatened, and that engine has stayed together so far. So,
well, what else do we have for questions for Darin? I want to let him go here pretty soon. This guy's a marathon. He's almost done the full 2 hours.
Is there anything that you'd like to address, Darin, that we didn't cover?
I'm sure there's a lot of things.
Yeah, son, there's years worth. I get it. I get where he's coming from. Well, we thank you for sharing the experiences with us, Darin. That is absolutely outstanding, and we very much appreciate it. We had some audio glitches twice, but I got a good clean recording. So what I'll do is I'll reload the recordings, video and audio recordings here tonight late, so that they're all nice and cleaned up and sound good and everything. But we had a little bit of audio glitchery at one point. So what else? Anybody else got questions for Darin? Going once, going twice, going 3 times? All right, we'll let him go. Go, sold. All right, Darin Morgan, thank you so much for joining us. Appreciate it, man.
You're welcome. It's been fun.